Today, for day 3 of circles, we're going to look at arc measures and properties of chords. So before we begin, here's some important vocabulary that you're going to want to pause this video and jot down. So a chord is a segment whose endpoints are on the circle. So if we look at this picture, there is a chord shown here where both of the endpoints are on the edge of the circle. The diameter would also then classify as a type of chord because its endpoints are on the circle as well. But our radius is not, because one of the endpoints is at the center, it's not on the edge. So looking at that picture, the chord and the diameter there are both technically fall under that category. A secant line, which is how you pronounce that word, a secant is a line that intersects the circle at 2 points. So it intersects, in this case, here and here. So we like to say a secant line touches the circle a second time. So that's just kind of a nice little way to remember what that represents. The difference between a chord and a secant is that the chord is the part that's inside the circle, and the secant is the entire line that goes on forever. A tangent line is a line that intersects the circle at exactly 1 point. So you'll notice we're going to call that point the point of tangency. And whenever we have a tangent line, there's going to be a special relationship between the radius and that point of tangency. And you might be able to tell just from looking at that picture that what is going to happen, and one of our properties we're going to learn today, is that every time a radius touches a point of tangency, there will always be a right angle formed. But again, I'm getting a little ahead of myself here, so let's just review our vocab. So what we want to do is we want to look at this picture and determine which of these terms do we see. So AC would be a radius of the circle. A to B is a type of chord, but more specifically, we know that that's the diameter because that chord goes through the center. D to E is a ray going from here to here. So that would be considered a tangent because it only touches the circle at point B. And last but not least, AE, the line running here, touches the edge of the circle twice and keeps going. So that is a secant. Coplanar circles, meaning circles that are on the same plane, can intersect once, twice, or not at all. So looking at these pictures, this first example here shows the different ways that we could have 2 intersections. The next one here shows that we've got 1 intersection, and when that happens, we call those tangent circles because they touch in one place, just like a tangent line touches the circle at one place. And if they don't intersect at all, they have no points of intersection. They can either be entirely separate from each other, like we see here, or it could be that they're concentric circles, which means they have the same center. Again, you've got some vocab here that you may want to jot down, and then we're going to move forward. So a common tangent is a line, a ray, a segment. It's any sort of tangent segment that is tangent to 2 circles at the same time. So notice we're touching the circle once here, we're touching the circle once here. That is a common tangent line between these 2 circles. Now if you look at these, there are multiple common tangents that we could draw, right? So for this one, we could draw another common tangent here. We could also draw it through the interior so that we're touching here and here, as well as this way, from here and here. So there's lots of different ways that we can have a common tangent. So looking at these different pictures, we've got 1, 2, 3, 4 different common tangent lines. So that is the maximum number of common tangents we could have for any 2 circles. Part B, or picture B, is going to have 3 common tangents. And I didn't do a great job of drawing that second one, but bear with me there. And 3 common tangents. This guy here is going to only have 2 common tangents. This one only has 1. And the last one, these concentric circles, do not have any. So all of your different choices are we can have 4, 3, 2, 1, or none of the common tangents. Now, like I said, this is going to be an important theorem today, so please make sure that you jot this down somewhere in your notes. But every time we have a tangent line, the radius and that point of tangency are always going to be perpendicular, meaning they're always going to form a 90-degree angle. So with that, it says in this diagram, PT is a radius, and we want to know, is ST a tangent or not? So it looks like it's only touching once, but maybe it's not. Maybe it's touching more than once. So to test that, this point of tangency and the radius should be forming a 90-degree angle. So I'm going to put a question mark inside of that 90-degree angle just to signify to myself, I'm not sure if that's true or not, because I'm trying to test that. So if that is a right angle, I should be able to use Pythagorean theorem to solve this question, because I've got the 3 sides of this triangle. Now, here is where you want to be careful, and I'll be honest with you, I don't love the way this picture is represented. That 37 looks like to me it's labeling that entire side because it's kind of hovering in the middle of that segment. But I 100% agree with you that you could argue that this 37 is only from here to here. And the part on the inside then would be the radius, which would be 12. But I will make absolutely sure on a test or quiz that you can tell what that's representing. Since that looks like that's the entire segment, we're going to use that as our C value. So it's 35 squared plus 12 squared truly equal to 37 squared. So I'm going to test that in my calculator. 35 squared plus 12 squared is 1,369. 37 squared is the same. So this would be yes, this is a tangent line. If those came out to be different numbers, we know that that's not a right triangle, so it would not be a tangent. So here, it says find the radius of this if we know we do for sure have a point of tangency. So again, this tangent line here is touching at one place. It's touching that radius. That's where that 90-degree angle is happening. So I'm going to say 80 squared plus r squared should equal 50 plus r squared. Now remember, when you square a binomial, to actually distribute that out or you'll lose that middle term. So I'm going to have 250 plus 50r plus 50r, that's 100r total, plus r squared, equals 80 squared plus r squared. And I can go ahead and fill that in here as well, just to have all my steps shown. Now at this point, it looks like I might have to factor because I've got a quadratic term. I've got a squared term. However, I have a squared term on both sides of this equation. So when I try to group them together, it's actually going to turn out kind of nice for me. They're going to cancel out. So now I just have to solve like I would any other equation. So I'm going to take that 6,400 and subtract 250. And then I'm going to divide by the coefficient of r. And I find out that my radius is 61.5. So with that, I've used Pythagorean theorem to solve for the radius of a triangle with a point of tangency. Another important theorem today is this one here, so make sure you jot that in your notes. Tangent segments from a common external point are congruent. So I've got a tangent line here, they're both intersecting at S. So what's important here is that both of those parts are equal to each other. So I kind of explain this 2 ways. Typically, if we teach this in the fall, we're kind of getting close to the holiday season. So if we look at that, kind of looks like we've got Santa's hat here. And we want both sides of that hat to be equal so that we have his hat standing up perfectly. Or if we're teaching this in the springtime, I kind of say think of this as if it were a bird, right? So that's its beak. We want those two parts to be equal. That one, however, falls apart a little bit because if you look at a bird closely, sometimes one beak is larger than the other, but you guys get my point. These two segments are going to be equal. So with that, we have two tangent lines with a common external point, which means that 28 should equal 3x plus 4, which means 24 equals 3x, which means x is 8. Same thing for these next two questions here. 2x plus 5 should equal, sorry, I left my squared off there. 2x squared plus 5 equals 13. Subtract that 5, 2x squared equals 8. Divide by 2, x squared equals 4. Now I'm going to take a square root of both sides, and technically, when I take a square root, I need to say positive or negative 2 because both of those are valid answers to that square root problem. And in fact, both of those are valid answers back in the question because if I go back here and I plug in a negative 2, because it's going to end up being squared, that's still a valid answer. It's going to give me a positive distance. Over here, 3x squared plus 4x minus 4 should equal 4x minus 1. Those 4x's are going to cancel out when I try to group them. So 3x squared equals 3. Divide by 3 on both sides. Take a square root on both sides. Again, when we take a square root, we technically need to say positive or negative. However, in this case, if I put a negative 1 here, I've got negative 5 for a distance. So in this case, my only valid answer is 1. These are common types of questions that the ACT likes to throw at you and that you may see on your state exam. So we're trying to find the perimeter of this triangle that is surrounding this circle. So we've got this circle inscribed. So remember, inscribed just means inside. So we've got a circle inside of a triangle so that it's perfectly touching one time for each of those points. And we want to find the perimeter. So remember the hats, right? So we've got kind of a Santa hat here. So I know if that's 10, so is this. Same thing down here. I've got 8 for both sides of that. And last but not least, over here, I've got 15. So for my perimeter, I've got 25. 15 and 8 makes 23. 10 and 8 makes 18. So I'm going to say 25 plus 18 plus 23. So my perimeter is 66 centimeters. I would recommend that you try this next one on your own, but I am going to give you a small hint to help you out. So start here first, where we've got this common tangent, or this hat, if you will. So we know that that's 1.9. And you can take the fact that you've got 3.4 minus 1.9 would give you 1.5. And then we can continue working around this figure. Come back once you have your answer and double check. Once I total up my perimeter here, I already know the total on the left, the total of the bottom, and the total of the right side. So across the top, I've got 1.6 and 1.9, which is a total of 3.5. So my final answer is 3.7 plus 3.6 plus 3.4 plus 3.5, which is a perimeter of 14.2 inches. One other theorem we're going to look at today. In the same circle or congruent circles, two minor arcs are congruent if and only if, remember that's that biconditional, which means they have to happen simultaneously. So two minor arcs are congruent if and only if their corresponding chords are congruent. So really what this is saying is that if we have two congruent chords, then this distance is the same as this distance. So the minor arc is congruent if the chord is congruent. So from here, if we look at our picture, it says circle P is congruent to circle Q. We know FG is the same as JK, and we know that the measure of arc JK is 80. That tells me that the measure of arc FG is also 80, because the chords are congruent. Down here at the bottom it says if AB is 110, that also tells me that BC is 110 because those chords are the same. So 360 minus 110 minus 110 tells me that I've got 140 left over for AC. Now they didn't ask for that, they asked for BC, so I would just say 110. Next question down here says, let AC be 150. So in this case, we've got 150 degrees out of the 360 that we've used so far, so that leaves us with 210 degrees. But because I know this arc is the same as this one, if I divide that 210 by 2, since there's two equal sections, I end up with 105 for each of those two arcs. Two other key components here that you're going to want to take a moment and jot down. If one chord is a perpendicular bisector of another, then the first chord is the diameter. Now all of these are pretty much saying the same sort of thing, so if you write just that one down, that should be enough to kind of help you out enough here. But our other pieces says, if a diameter of a circle is perpendicular to a chord, then the diameter must bisect the chord and its arc. So those are our two key pieces here that you're going to want to write down. So with that, since we see that we've got a 90-degree angle interacting with the diameter, that tells me that this arc is the same as this arc. So 9x should equal 80 minus x, which tells me that x is 8. So when I go back, C to D is going to be 9 times 8, which is 72 degrees. D to E is 80 minus 8, which is another 72 degrees, but they should be equal, so that makes sense. And then from C to E, remember that when we use two letters, that's the minor arc. So we're just combining those together. 72 and 72 makes 144. One more theorem. In the same circle or congruent circles, two chords are congruent if and only if they are equidistant from the center. Meaning, if I've got this chord as 16 and this chord as 16, they have to be the same distance from the center, which means 2x would have to equal 5x minus 9, so negative 3x equals negative 9, which means x is 3. Where you have to be careful, they do not ask for x, they ask for cu. So I'm going to come back here, 2 times 3 tells me that cu is 6. Lots of theorems today, guys, but a lot of just equalities here. So find the value of x and explain your reasoning. So for the first picture, we have a diameter with a 90-degree chord. So in other words, we have a perpendicular chord to the diameter. That means that that 4x would have to equal 3x plus 7. Now I know that you guys could solve that, so once I set these up, I'm just going to move to the next one. We have a similar situation for the next question where we have a diameter and a perpendicular chord. So I know that those two parts are equal. For the next piece here, I've got one radius labeled as 6x plus 9 and another radius labeled as 8x minus 13. I know that a radius inside of the same circle is always equal, so I can set those equal to each other. Now I have one chord that is equidistant away from the center to another chord, and I can see that with that congruency marking here, which means 18 should equal 5x minus 7. Same thing here, I've got one chord that's the same distance away from the center as another chord. However, where I want to be careful is they only give me this part of that chord. So I would have to double that so that I have 6x plus 4 would have to equal 22. And last but not least, we've got two congruent chords, so they must be the same distance from the center, which means x plus 8 would have to equal 4x plus 1. For these next three pieces here, we're just kind of summarizing some things that we know. So remember, if we have a central angle, the central angle is the same as the arc measure. So all in all, I have 5x minus 5. That would have to equal 360 degrees. Same thing for the next one, x squared plus 5x plus 36 plus 10x would have to also equal 360. And then last but not least here, since this guy is representing 4x, I'm going to have to think through how do I use that to help me find what's missing. So looking at the information that I currently have, since this radius is equal to this one, I could also put a 4x here. So basically now I have an inscribed angle with a 4x. And I know that an inscribed angle with its vertex on the edge is supposed to be half of the arc. So if I double that to say 8x, it should equal the x squared minus 5x. So just a couple of review problems here from a previous day's notes. These last few questions here are going to go pretty quickly. Just a reminder, if we have this chord that is perpendicular from the center of that, automatically those values are the same. So looking at this guy here, that x is the same. Next few questions, take a look closely at what you have. We know that the diameter is 31.8. So if I divide that by 2, that tells me that my radius is 15.9, which means the distance from here to here should be 15.9. So if I subtract that 7, x is 8.9. Number 4 is very similar, so give that one a try on your own and then double check. All of my radii are 9.7, so from here to here should be 9.7. So 9.7 minus 5.1 leaves me with an x value of 4.6. Number 5, same thing, 25.2 cut in half gives me a radius of 12.6. 12.6 minus the 4.5 I already have tells me that x is 8.1. One more, try this one on your own and then double check with us here. Radius of 9.4 minus 4.2 tells me that x is 5.2. Guys, these are all of our notes for today about tangents and chords. Please email me if you have any questions or concerns.